This is your instructor, Muhammad Hawa. Good morning. Let's talk about complex numbers, a very important topic for this course and other courses as well in electrical engineering. You're probably familiar with real numbers because real-time signals or practical signals which we can manipulate by physical hardware can be expressed using those real numbers. And we typically visualize the set of real numbers using a one-dimensional horizontal axis, as you can see here, where we see the numbers 0, 1, 2, 3, -2. We also see the rational numbers like -3/7, or the irrational numbers like square root of 2 or pi, and so on. Those, of course, belong to the set of real numbers. However, we can solve a wider range of mathematical problems, such as this quadratic equation, x squared equal -1, if we introduce something called imaginary unit, or the imaginary operator, which is typically denoted by I in mathematical textbooks or by J in electrical engineering textbooks. Here I'm going to stick with J for the imaginary unit or the imaginary operator. We define the imaginary unit using this equation. We say by definition J squared is equal -1. So J is something that we square, we get -1. Of course, you know this is not a real number, because if you square any real number, positive or negative, what you're gonna get is a positive result. However, J is imaginary. It's something new that we define, and we say it's something that if you square, you're gonna get -1. Of course, this means that J is the square root of -1. Please memorize this or this. This is the definition of the imaginary operator or the imaginary unit J. By the way, if I ask you to calculate J to the power 3, it's very easy to do, because J to the power 3 is simply J squared multiplied by J. And we know by definition that J squared is -1, so it's -1 multiplied by J, and this tells you that J to the power 3 is simply -J. How about J to the power 4? Well, J to the power 4 is J squared multiplied by J squared, and J squared is -1, multiplied by J squared, that's -1. You're gonna get J to the power 4 is equal 1. You can keep going. You can easily prove that J to the power 5 is equal J. J to the power 6 is equal -1, and so on and so forth. Now that you understood the imaginary operator, let's move one step further. The product of a real number and the imaginary operator is what we call an imaginary number. For example, if you multiply 5, that's a real number, by J, the imaginary operator, you get J5. That's what we call imaginary number. Same thing here. If you take -0.35, that's a real number, multiply it by J, you're gonna get the imaginary number -J.35. Okay, now we have real numbers and we have imaginary numbers. The sum of a real number and an imaginary number is what we call a complex number. Thus, a complex number, capital A, is equal to A, that's a real number, plus JB, that's an imaginary number. If you add up this real number plus this imaginary number, you're gonna get this complex number. Usually we try to represent the complex number with a special notation so that you can easily recognize this is complex number. Sometimes we use boldface, sometimes we use vector notation like you see here, sometimes we use over bar, sometimes we just use a capital letter to indicate a complex number, where we use a small letter to represent real numbers. The important thing is, usually you'll see different symbols for complex numbers versus real numbers so that you can clearly see the difference. Please understand that both A is real number and B is real number. However, because we multiplied B, which is real number, by J, we got imaginary number. Because we added imaginary number plus a real number, we got a complex number. We say that the complex number consists of two parts. It has a real part, that's A, and imaginary part, that's B. The notation goes like this. We say the real part of the complex number, capital A, is equal this real number, small letter a. On the other hand, the imaginary part of the complex number, capital A, is equal the real number b. I hope you're not confused by this terminology. Imaginary part is different than imaginary number. The imaginary part of A is the real number of B. not the imaginary number JB. JB is the imaginary number, while B is the imaginary part. Hence, an imaginary number should not be confused with an imaginary part. A few things to keep in mind when you work with complex numbers. A real number can be considered a special case of a complex number that has an imaginary part equal 0. So if you are given a real number A, you can easily say, well, this is also a complex number, A plus J0. But the imaginary part of this complex number is actually the special case of 0. Similarly, an imaginary number can be considered a special case of a complex number that has a real part equal 0 this time. So if I give you this imaginary number JB, you can easily say this is also a complex number equal 0 plus JB, where the real part of this complex number is 0. It's a special case. Please notice that B is the imaginary part, JB is the imaginary number, and 0 plus JB is the complex number. By the way, the word complex number here does not mean complicated or impossible to work with. All it means is that the complex number is composed of several parts. There is the real part and there is the imaginary part. We use the word imaginary to describe the imaginary operator J, which is the square root of -1, because we cannot create the square root of -1 in real life. If you write the complex number as the sum of real number A plus imaginary number JB, we say this complex number is written in the rectangular form, or we call this the rectangular representation, or the Cartesian form of the complex number. We have other forms like the exponential or the polar forms. They describe the same complex number, but they look slightly different versus the rectangular form. When working with complex numbers, it's helpful to visualize the complex number graphically. And to do that, we use a rectangular or Cartesian coordinate system, which has a horizontal axis for the real numbers. You can see here the numbers 1, 2, pi, negative numbers, and so on, exactly the same as the axis describing the real number set. However, we have an additional axis here, the vertical axis for imaginary numbers, where you can see J1, J2, J3, minus J1, minus J2.5, and so on. This two-dimensional plane created by the horizontal axis and the vertical axis is actually called the complex plane or the Argand diagram. And we represent a complex number in this complex plane as a single point. For example, if I want to visualize this complex number, capital letter A, equal 2 plus J3, then I use this point in the complex plane to represent this number. This point here, see, has a projection on the horizontal axis, the real numbers equal 2, that's 2 here, and it has a projection of J3 on the vertical axis or the imaginary axis, that's because of this plus J3. If I say represent the complex number capital B, 3 minus J in the complex plane, then you go to this number 3 here for the real number and minus J1 for the imaginary number, and then you draw this point. This point is a visual representation of the complex number B. Sometimes you'll see people represent the complex number in the complex plane as a line or as a vector, since the behavior of complex numbers reminds us of the behavior of two-dimensional vectors. For example, you see I represented this complex number A as a line at 2 plus J3, and this complex number B as this line at 3 minus J. However, please remember that complex numbers are not actually vectors. However, complex numbers exhibit a very similar behavior to two-dimensional vectors, and that's why if you think about a complex number as a vector, then it's easier to memorize the properties of complex numbers. A quick reminder, we call A plus JB the rectangular form or the Cartesian form of the complex number because we can visualize that complex number in the rectangular or the Cartesian coordinate system. Now let's talk about some properties and some mathematical operations we can perform on complex numbers. First, equality. We say that two complex numbers are equal if and only if their real parts are equal and also their imaginary parts are equal. So two complex numbers are equal to each other if their real parts are equal to each other and their imaginary parts are also equal to each other. Now that this is out of the way, how do we add two complex numbers? To obtain the sum of two complex numbers, add the real parts of the two complex numbers, which gives you the real part of the result, and also add the two imaginary parts to get the new imaginary part. Say I want to add this complex number capital A plus this complex number capital B. And let's say that A is equal A plus JB, this is a complex number. And let's say that this complex number capital B is equal C plus JD. Take this real part, add it to this real part, you get the resulting real part A plus C. And add the imaginary part B plus the imaginary part D, you're gonna get the resulting imaginary part B plus D. So the result is A plus C plus J, B plus D, and you get the resulting complex number. For example, if I say add the complex number 2 plus J3 with the complex number 3 minus J, you're gonna add this real part 2 plus this real part 3, like you see here, you're gonna get the real number 5. You are also going to add the imaginary part 3 plus the imaginary part here minus 1, like I did here, you're gonna get 2, and the final answer is the complex number 5 plus J2. By the way, just like vectors, we can do addition and subtraction of complex numbers graphically using the complex plane. For example, if I say add this complex number A, which is 2 plus J3, plus this complex number B, which is a 3 minus J, what you can do is draw a parallel line to A here and a parallel line for B here. You get this parallelogram, and this line is A plus B, which as you can see is equal 5 plus J2. Another graphical method to add the two complex numbers is to move B from its location to this location here. So you get the head to tail shape, and that result is A plus B, which is also 5 plus J2. Adding complex numbers graphically can be quite helpful sometimes, even though I'm not going to do it too much, because calculators nowadays can easily handle adding and subtracting complex numbers. If you want to do subtraction, say I want to subtract A minus B, where A is equal A plus JB and B is equal C plus JD. I need to subtract the real parts. I'm going to get A minus C for the real part of the result, and I want to also subtract the imaginary parts, so I say B minus D is my imaginary part of the result. For example, 2 plus J3 minus 3 minus J, take 2 minus 3, that's the real part, which is minus 1, and take 3 minus minus 1, that's the imaginary part you see here, which is equal 4. So the result of the subtraction is minus 1 plus J4. Addition and subtraction of complex numbers is quite simple. How about multiplication? The product of two complex numbers is obtained by expanding the product of sums, since multiplication distributes over addition. For example, let's try to multiply the complex number A by the complex number B. Notice, by the way, I could represent multiplication like this, AB, or A cross B, or A dot B. We only have one multiplication in complex numbers, unlike vectors where dot product is different than cross product. Here, in complex numbers which are not vectors, multiplication is just multiplication. Where if you want to multiply the complex number A plus JB by another complex number C plus JD, then what you want to do is multiply A by C, and the result is a real number AC, and then you add JB multiplied by JD. Please remember that JB multiplied by JD is J square B multiplied by D. But I told you that J square is minus, so the multiplication is actually minus BD, which is a real number. So I put minus BD here, which is the multiplication result of JB by JD. And then you want to say A multiplied by JD, that's JAD, plus JB multiplied by C, that's JBC. So the final answer is a real part, which is AC minus BD, and an imaginary part, which is BC plus AD, and that is the complex number resulting from multiplication. Let's solve an example. Say I want to multiply the complex number 2 plus J3 times the complex number 3 minus J. I'm going to multiply 2 by 3, that's 6, and then multiply j3 by minus j. That's minus j squared 3, which is plus 3. And then I'm going to multiply j3 by 3, that's j9, plus minus j multiplied by 2, that's minus j2. And those two are 9 minus 2, so they give you j7. 6 plus 3 gives you 9, and the answer of the multiplication is 9 plus j7. Multiplication takes a little bit of time, but it's not difficult to obtain the result. By the way, most probably your calculator can multiply the two complex numbers and give you the answer even quicker. The next topic is complex conjugate. The complex conjugate of a complex number a, which is equal a plus jb, is by definition a star. When I write a star, it means complex conjugate of the number a. What is the complex conjugate of this complex number? You want to switch the j into minus j. It's equal a minus jb. For example, if I give you a complex number 2 plus j3 and I say find the conjugate of that complex number, you say it's 2, you keep the real part the same, and then you put minus in front of the j, you get 2 minus j3. The complex conjugate of a 3 minus j, you put minus in front of the j here, you're going to get a 3 plus j. That's the complex conjugate of the complex number b. Later on, God willing, I'm going to tell you that complex conjugate operation keeps the complex number magnitude the same while changing the sign of its phase. But let's keep this for a later point in time. For now, please remember that the complex conjugate for a full complex expression is obtained by replacing every complex term in the expression by its conjugate, or by replacing every j in the expression by minus j. It's also worth remembering the following properties of a complex conjugate. If you add a complex number plus its complex conjugate, what you're going to get is a real number that is twice as much as the real part of the original complex number. You can easily prove that this is the case. Let's add a plus jb plus its complex conjugate a minus jb. You'll see that this jb will cancel out with the minus jb. You end up with 2a, that's 2 times the real part of the complex number capital A. What if I subtract a minus its complex conjugate? You're going to get a plus jb minus a minus jb. Now a cancels out with the a here. jb minus minus jb, you're going to get 2jb, which is an imaginary number equal j multiplied by 2, the imaginary part of the original complex number. Now try this one out. Let's multiply a complex number a by its complex conjugate. This will be very useful in a minute. What you're going to get is a plus jb multiplied by a minus jb. A multiplied by a, you're going to get a square. jb multiplied by minus jb, you're going to get minus j square b square, which is simply a plus b square. It's a real number. Now multiply jba, you're going to get this. Minus jba, you're going to get this. The last two terms cancel out. You're going to end up with a result equal real number, and that real number is equal the real part square plus the imaginary part square. This will be very useful to us in a second. Finally, an interesting property. What is the complex conjugate of the complex conjugate? If you take a equal a plus jb and you find its conjugate a minus jb, and then you take the conjugate again, what you're going to end up with is a plus jb, the original complex number. So if a star is the complex conjugate of a, then a is the complex conjugate of a star. This is a very simple result. Why did I tell you about complex conjugate? Because it's going to help us in dividing two complex numbers. Please remember that the quotient of two complex numbers can be easily found by multiplying both the numerator and the denominator by the complex conjugate of the denominator. For example, if you divide a by b, where a is a plus jb and b is c plus jd, you can easily find the result if you multiply both the numerator and the denominator by b star, the complex conjugate of the denominator. Notice here I multiply by b star and divide by b star. I didn't change the result. However, when you multiply this b by its complex conjugate, what you're going to get is a real number, which simplifies the division. Let me go through it step by step. If I multiply b by its complex conjugate b star, so I multiply c plus jd by c minus jd, I told you a minute ago that you're gonna get a real number, and that real number is c squared plus d squared. Of course, you have to do the extra step of also multiplying complex number a by the complex conjugate of the complex number b. So you want to multiply a plus jb by c minus jd, and the result is a multiplied by c plus minus j square bd, that's b multiplied by d, plus j b multiplied by c minus d multiplied by a, and this means you have a complex number divided by a real number. And then I can easily break this down into two parts. The first part is ac plus bd divided by the denominator c square plus d square plus j. You take this imaginary part bc minus ad divided by the common denominator, which is c square plus d square, and that is the result of your division. Let's do a numerical example. I want to divide the complex number 2 plus j3 by the complex number 3 minus j. How do I do that? Take the complex conjugate of the denominator 3 plus j, multiply it here and multiply it here. When you multiply 3 minus j by 3 plus j, you're gonna get 3 multiplied by 3, that's 9, minus j multiplied plus j, that's minus j square, which is actually 1. So you're gonna get 9 plus 1, that's a real number. However, if you multiply j by 3 minus j by 3, those two terms will cancel out. You don't get any imaginary part. However, for the numerator, we're going to multiply 2 by 3 equals 6. And then you're going to multiply j by j3. That's j squared 3, which is actually minus 3. And then you're going to multiply j3 by 3. That's j9. J multiplied by 2, you're going to get j2. And then add up 6 minus 3, you're going to get 3. j9 plus j2, you get j11. Divide this complex number by the real number 10. You're going to get 3 over 10, that's 0.3. 11 divided by 10, that's 1.1. This is the answer of division, which I know is a bit cumbersome. And that's why I'm going to tell you later on to do division in the polar form of complex numbers instead of doing division in the rectangular form. You can do it in the rectangular form, but as I have shown you, it takes a little bit of time and effort. Alright, now that we have understood addition, subtraction, multiplication, and division, you might be wondering, why bother with complex numbers? Why spend this much time and effort doing those operations using complex numbers? Well, we have reasons for that. Complex numbers represent a valuable mathematical tool to simplify calculations in some areas of engineering analysis and design. So actually we use complex numbers not because they're more difficult, but because they simplify difficult problems. I'll give you a couple of examples. You'll probably take a course in circuit analysis where you work with AC systems, alternating current systems. If you work with electrical AC systems and you use inductors and capacitors, you will discover that as you try to solve your problem, you'll end up with a set of differential equations. Mathematically speaking, we can solve a set of differential equations, but usually this problem is not as easy to solve. So clever people thought about how can we simplify the problem. And what they're going to tell you in circuit analysis, let's convert voltages and currents into something called phasors. Those are complex numbers. And let's convert the resistance and inductance and capacitance into something called impedance. Those are also complex numbers. So we move from using real numbers into using complex numbers. Because if you do that, those differential equations will be converted into a set of linear equations. And we know that solving a set of linear equations is way much easier than solving a set of differential equations. And that's why we do the conversion. Not because complex numbers are going to make it more difficult for us. Rather, complex numbers will simplify the problem, and instead of working with differential equations, you're going to work with linear equations. Of course, after you finish solving the problem, you can also easily convert back the phasors and impedances into the original elements, and you get your answers in real numbers. So even though what we're looking for are those real valued answers, what we do is convert into complex numbers so that the problem we're facing is easier, and then we convert back to the original answer. It turns out that converting to complex numbers plus solving the answer using complex numbers plus going back is way simpler and faster than solving using real valued numbers, especially after you've gotten enough practice using complex numbers. In addition, we're lucky today because calculators and computer software has widespread support for complex numbers, so you don't even have to multiply and divide by hand like in the good old days. What you can do is plug in those numbers into your calculator and it will give you the answers very quickly. Here I show you another example why complex numbers are useful. If you work with filter design or you are designing communication systems, which by the way use a lot of filters, then you will probably encounter convolution. You can of course do convolution using real numbers. This is possible, but it's not that easy. That's why we convert our signals, input and output signals, and we also convert the system response, the filter response, using Fourier transform into what we call frequency domain. And frequency domain typically uses complex numbers. Why do we do that? Because instead of working with convolution, if you do Fourier transform, what you're going to get is multiplication. And multiplication is way easier to solve, way easier to visualize than convolution. Once you obtain the answers using Fourier transform, you can go back to the original time domain and convert your answers to real numbers using something called inverse Fourier transform. The Fourier transform solution and inverse Fourier transform is way easier than convolution. That's why we teach complex numbers. It's actually a mathematical tool that makes life easier for the engineer. When we work with complex numbers, we often encounter a very important fundamental identity, which is known as Euler's identity. You will see that we can express this identity in 4 different forms. All those forms are very important. Please remember all of them because we'll need them later on. The first form for Euler's identity says that you can express the exponential e to j theta, where j is the imaginary operator, as the sum of cosine theta plus j sine theta. This is the first form of Euler's identity, which says there is a real number here plus imaginary number here is equal exponential of the imaginary number j theta. If you introduce a minus sign in the exponent here, so you get e to minus j theta, this is equal to cosine theta minus j sine theta. By the way, if I add this plus this and divide by 2, so e to j theta plus e to minus j theta divided by 2, this will cancel out and what you're gonna get is cosine theta. Similarly, if you say e to j theta minus e to minus j theta and then you divide by 2j, the cosines will cancel out after subtraction and what you're gonna end up with is sine theta. All those forms are very important. Again, please remember them. They will be helpful later on. I'm going to show you the proof very quickly. Start from Taylor series. Try to expand cosine theta. What you're going to get is this 1 minus theta square over 2 factorial plus theta to the power 4 over 4 factorial minus and so on. On the other hand, if you try to expand sine theta using Taylor series, you're going to get theta minus theta to the power 3 over 3 factorial plus theta to the power 5 over 5 factorial and so on. Notice here you get even, here you get odd. Now what if I add cosine theta plus j sine theta? I'm going to get 1 here plus j theta. I'm going to get minus theta square over 2 factorial. For this I'm going to get minus j theta to the power 3 over 3 factorial plus and so on. However, if I use Taylor series and expand e to gamma, what I'm going to get is 1 plus gamma square over 2 factorial plus gamma to the power 3 over 3 factorial and so on. So I'm going to get the even parts and the odd parts. Like I'm getting here the even parts from the cosine and the odd parts from the sine. Of course, all you have to do is take the Taylor series expansion and substitute gamma equal j theta. The result is e to j theta equal this much, which we've seen a second ago, equal cosine theta plus j sine theta. So the proof that e to j theta is equal cosine theta plus j sine theta is very simple. If you want to prove the part e to minus j theta, then substitute gamma equal minus j theta. You'll see that e to minus j theta is equal cosine theta minus j sine theta. those are the two first forms for Euler's identity. If you want to prove the last two forms of the Euler's identity, then try adding and subtracting the above two expressions for e to j theta, which is this, and e to minus j theta, which is this. You will easily obtain the last two forms of Euler's identity. But more important than the proof is using this Euler's identity to our advantage, which I'm going to do in the second part of this video about complex numbers, where I'm going to define the exponential and polar forms for complex numbers. Until then, if you have any questions, please leave them in the comment section. See you later. Goodbye.